Hello there. So today we're going to go over one of those canonical computer science algorithms called Dijkstra's algorithm or Dijkstra's algorithm. I'll probably go back and forth. I've heard it pronounced both ways. I think normally I default to Dijkstra's. And I can't just sort of introduce it just with that, so I've got the flashy Dijkstra shortest path algorithm here. And I do want you to try to remember this as Dijkstra's single source shortest path algorithm. So later on, if you're in an interview, if you remember the full title of this thing, Dijkstra's single source shortest path algorithm, you remember what it actually does as opposed to just it's a graph algorithm. So single source means we have a start vertex and we're trying to find the shortest path from that start vertex to every other vertex. The plan for this set of slides is to discuss sort of a somewhat new concept here. So if you've watched the videos on graph representation, it's not completely new, but we're going to introduce our first algorithm that needs edge weights. So that's saying that there's some quantity associated with each edge. We're going to discuss shortest paths again. We've covered that once before. And we're going to talk about a proof for Dijkstra's algorithm. Okay, so what is Dijkstra's algorithm? It's for finding the shortest path from a start vertex to every other vertex. So if I say that the yellow dot here is the start vertex, I want to find the shortest path from this one to every other one. And let's say you're doing, GPS navigation, and you really only care about getting to this certain location. Well, once you find the shortest path to that location, you can stop the algorithm short. So maybe we don't actually have to compute the shortest cost to other things that are further away. So yeah, you can halt this algorithm early if that's useful. You can think of this as being useful for network routing, for path planning, and I think this one's it's pretty easy to think about applications for this algorithm, so I won't belabor the point too much. But watch this animation. So this is what Dijkstra's does. In each iteration, you'll see that another green line is sort of drawn. So each iteration, we find a new vertex, and we find the shortest path to that vertex. You might notice that it's not necessarily the path links that we go by. So I've got one circle down here, sort of towards the bottom left, that shows we don't always take the shortest edge if that's even if that path is available. Sometimes it makes sense to continue on and look at other vertices because the total path to those other vertices is shorter than the path to another vertex, even if that other vertex has the shortest edge getting to it. And that's something we'll come across several times here. So if that wasn't a great explanation, don't worry about it too much. All right, so here's our definition of Dijkstra's algorithm. As an input, we're going to have a weighted graph. So again, this is our first application of having weights for our graph. And all that really means is that if you look at a single edge, instead of it just being, an edge from A to B, it's also going to include some weight information. So maybe this has a cost or a weight C. And Dijkstra's also needs a start vertex, just like depth first search did and breadth first search did. And our output is for all vertices in V, we're going to output the length of the shortest path from S to V. We can also output the actual path, but for the purposes of our lecture slides here, we're just going to worry about the length of the path for now. So for example, if I have A, B, C, and this is 3 and this is 4, you might imagine to get to C from A has a total cost of 7. We'll just output the 7 and not worry about the fact that the path goes A to B to C. That's something that we'll talk about later on when we look at another algorithm for solving this problem. Our assumptions for Dijkstra's are that a path exists from the start vertex to every other vertex. This isn't too large of an assumption because it's pretty easy to check. So how can we check for this property before running Dijkstra's algorithm? Well, if you remember our discussion on the connectivity algorithm, so breadth first search and depth first search, you know that's exactly what they do. So we can use one of those algorithms just to check that property, and if it doesn't, if there's not a path from S to another vertex, well, we can either remove that other vertex or try to find a way to connect that vertex. And our much heavier assumption here for Dijkstra's algorithm is that all edge weights are non-negative, so they're 0, greater than or equal to 0. Okay, so this is what a graph has normally looked like for us. And what we're adding here are these costs between each edge. So again, we could denote this one as the SV edge with a cost of 1, or the VT edge with a cost of 6. So we might ask a question like, what is the shortest path length from S to all other vertices? Well, starting at S, we have two choices for the next vertex we might look at. So looking at the cheaper of those two edges, we could say that the shortest path from S to V is 1. So that has the shortest path length of 1 to get to V. How about to get to W? Well, to get to W, we have two different ways in. We could come in through V, or we could come in through S. And previously, we would pretty much always say that you should just take the path from the closest connected, the fewest number of hops. But here we can see that that S to W edge has a cost of 4, whereas if we go through V, we have the cost to get to V, which is 1, plus the cost to get from V to W, which is 2, which gives us a total cost here of 3. And then finally T, we have two different ways into that. And we'd be comparing 6 plus 1, which is 7 up here, and comparing that to 3 plus 3, which is 6 down here. So the cheapest cost to get from S all the way to T is going to be 6. All right, so we did talk about this problem once previously in the semester. So how did we compute the shortest path before? We used a breadth first search. How can, the next question would be, how could we modify that breadth first search process to work with graphs that have weighted edges? And there's a number of ways to do it. I'm going to put a pause in the video here just so you have a chance to think about it before I give the answer. Well, one thing we could do is, let's say we have an edge that looks like this going from a vertex A to a vertex B. We could just expand that edge and add some sort of fake nodes in the middle, which is what I've done here. So this would be A, and this would be B. And then we just have a couple of pseudo nodes in the middle that we don't really care about, but we can now use a breadth first search and sort of explore in layers, and we'd see that 1 to get to that pseudo node, 1 to get to that pseudo node, and you know what do you know, 3 to get over here to B, and that's the cost we had before. So what is the problem with this approach? Why would we not necessarily want to do that? Well, we know that breadth first search is a big O of n plus n algorithm. But what happens when we explode the number of vertices? This algorithm starts to feel less linear. So for example, what if it's useful to have A, B, and I don't know, a really large number here? You can imagine it makes sense to find another way to do this that just directly takes into account the edge weights, which is what Dijkstra does. Another reason we might not want to do this is what happens if we have fractions here. It gets a little bit harder. I guess you can do a multiplication and round everything up to a whole number. So like turn this into a 17, for example, but then we run into the same problem as before.